And today's speaker is Noah Lupu-Gladstein, who is one of my favorite collaborators. He's working on quantum optics in the lab of Ephraim Steinberg at the University of Toronto. And one of the reasons for my liking Noah particularly much is that he specializes in looking at fundamental quantum phenomena, so things that we usually look at from a theoretical setting, but he's doing it for real in the lab. So I just have some like kind of a few titles from Noah's papers on the archive from recent years, and you find stuff like experimental comparison of Bohm-like theories with different ontologies, or more funky papers like do qubits dream of entangled sheep? And very recently, just I think 2 days ago, Noah put up a paper called Negative Quasi-Probabilities Enhance Phase Estimation in Quantum Optics Experiments. So today, Noah is going to tell us about his super exciting work on quantum metrology and phase estimation. Thank you very much for agreeing to wake up at this ungodly Canadian hour to come and tell us about your research, Noah.
Thanks so much for having me, David, and happy to be here virtually at least. Maybe one day I'll be able to travel the world again. So thanks for the great introduction. I'll go ahead and start putting my slides up here. So as David mentioned, the title for this talk and the paper that I'm sort of presenting off of today is Negative Quasi-Probabilities Enhance Phase Estimation in a Quantum Optics Experiment. Quite a mouthful, but we'll dissect what all those mean. And I want to just get started today by, well, David already introduced me, but I want to thank my collaborators. So Batuhan in particular sort of was putting an equal amount of work on this paper as I did. Then, of course, David also put in his own hefty share of theory prowess on the paper. We had Aaron Brodich, Arthur Pang, Ephraim Steinberg is my supervisor, and then Nicole Younger Harburn as also sort of a supervisor on this paper. So then we have all these wonderful sponsors that I'm sure I forgot some of them, but these are the ones that I managed to remember for the purposes of this talk. So let's get on to it. All of the references for today's talk can be found in our archive posting that was a few days ago. So I'll leave that to you guys to delve into more deeply if you want to learn more. So the way this talk is going to go is first, I'm going to make an important distinction between different types of uncertainties in quantum mechanics and really just generally. Then I'm going to tell you about something called parameter estimation, which is a particular task that quantum resources can be really helpful for. Then I'm going to introduce something new for this work called partially post-selected amplification, which is a tool that you can use to increase your performance at parameter estimation. And it utilizes some foundational aspects of quantum mechanics. Then I'm going to introduce a quasi-probability representation of incompatible observables. I'm going to show how that representation helps explain the success of partially post-selected amplification. Then finally, I'll end by showing that there is this interesting equality between metrological enhancement provided by partially post-selected amplification and negativity in this quasi-probability distribution. And before I go any further, I'll just mention that I find that this is always more fun, more interesting if it's more of a dialogue. I know it's difficult over Zoom, but if at any point you have some questions or want to speak up, feel free to go ahead and try and ask a question or unmute yourself, put yourself on video. So yeah, don't be shy for asking questions. We can take those in the middle. Okay, so broadly speaking, it's useful to distinguish two different types of uncertainty. So on the left, there's statistical uncertainty, and on the right, we have intrinsic uncertainty. These names are not really standard names. I'm just using them for the purpose of this talk. But what I mean by statistical uncertainty is you're trying to measure something, there's some distribution. You have some ignorance about the quantity that you're trying to measure, but you have many copies of that thing. And so you measure over and over and over again. And as you measure more, your uncertainty goes down, like 1 over the square root of the number of trials. And in principle, the thing that you're trying to measure is known by someone, but you're just ignorant of it, and you're trying to reduce your uncertainty by getting a lot of statistics. Another type of uncertainty is something that here I'm just calling intrinsic uncertainty, but it's something that having more and more trials will not really help you with. So classic example is a wave packet has some uncertainty relation between its position and its momentum. And that single particle on its own, you can measure it once, but no extra information out there will really help you, will let you break this Heisenberg uncertainty relation. So these two things are separate from each other. But what I want to show is that you can actually exploit this intrinsic uncertainty to more efficiently reduce your statistical uncertainty. So this was something that maybe is not obvious, but first came to my attention a few years ago when Nicole and David, two of the collaborators on this work, posted a paper to the archive a few years ago now, claiming that a certain foundational phenomena in quantum mechanics related to intrinsic uncertainty, incompatibility of certain observables, would actually let you improve your statistical uncertainty. And that paper was kind of more of an existence proof rather than a concrete prescription of how you might go about doing this. And they reached out to me and they got me interested in this experiment and the ideas behind it. And so I was wondering if we can maybe do an experiment to show how to sort of put this into practice more concretely, and also how much advantage is actually practically possible. So this opened up a few lines of questions. One was, is it actually possible to do this experimentally at all? Maybe there's just some caveat that we're missing. And so that there's a question, extremely relevant for your project. Okay. So how much improvement is practically possible? And then we want to know how does the improvement depend sort of quantitatively on intrinsic uncertainty, and how do we even go about quantifying this thing I'm calling intrinsic uncertainty to begin with? So let's start by just going over what I mean by parameter estimation. So in the sort of pared down spherical cow version of parameter estimation, we imagine that we have two parties, Alice and Bob. Alice deterministically from some dial picks a value for this parameter, let's call it theta. And she then sends that parameter over to Bob, but it gets sent through a noisy channel. And so Bob doesn't receive the actual value of theta, he receives some random variable x, which depends in some way on theta. And so Bob's goal is to give the best guess to theta that he can based on the value of this random variable that he gets. So we're gonna practice this concept of parameter estimation. There's going to be a few demos that happen throughout the talk. They're going to get progressively harder. So let's just start with this easy one. I have two images, one image on the left and one image on the right. And each image, there's a mean pixel intensity somewhere between 0 and 1. I know I set what the mean pixel intensity was, but you are observing random values. And so your goal as a parameter estimator would be to guess the mean intensity of these two images. But that's going to be pretty hard for you. So to make it easy, I just want you to guess whether the left one or the right one is darker on average. Okay, so think about it for 10 seconds. After 10 seconds, when you've made your final decision, you've all officially become parameter estimators and have taken your first step towards experimentalists. All right, so that's an easy one, but we'll come back and it'll get progressively harder. But this is the main idea behind parameter estimation. Now, parameter estimation comes in many forms in the real life, but the sort of paradigmatic example of it in quantum optics is phase estimation. So in phase estimation, again, this is the very spherical cow version of it. Everything's sort of pared down and made neat. We have some Hermitian operator A, which you can think of as being like your Hamiltonian that generates translations in time.
Sorry to interrupt, Noah.
Yeah.
So I think my Wi-Fi is a bit shaky, so I'm not sure if it's because of that or if the slide has not changed. Now it's changed for me. Okay, maybe it's just for me. So if the slide doesn't change for anyone else than me, please write in the chat. But I think it's probably just for me.
Okay.
I think it must be just for you. It changed immediately for me.
Okay. Okay. Thanks, Crispin.
Yes.
So in phase estimation, we have some Hermitian generator A, which you can think of as being like Hamiltonian. We would start with some initial state. So here I'm imagining we're in some phase space I can conceptualize as some kind of 2D circle. After some time, my initial pointer state will have evolved and now be deflected by some angle theta. And at the end of this experiment, I'll do some kind of projective measurement indicated here by this red arrow. And I'll get sort of a yes or no answer from that projection, the probability being related to sort of geometric distance, actual geometric projection of this rotated state onto my projected state. And so phase estimation like this describes a lot of real world problems that have a lot of great scientific interest. So for example, the people measuring gravitational waves at LIGO are doing essentially this all day long. They're measuring the phase of some giant kilometers long interferometer. People at NIST doing atomic clocks are doing phase estimation when they're telling the most accurate time known to humanity. That's just phase estimation. So this has wide-ranging applications throughout precision measurement. What we're going to do, and what we've done, is to do a very simple pared down version of this phase estimation type of experiment. So this is polarimetry, which means that we're measuring a phase between two axes of a crystal, the birefringence of that crystal. So the goal for us is going to be to measure a crystal's birefringence, basically the difference in the speed for light oscillating along one direction versus another direction. So the way the start of this experiment looks like is that we have two orthogonal modes. We have horizontal polarization 0, vertical polarization labeled as 1. We have a single photon source at 808 nanometers. We prepare a pure polarization state. It gets fed over to this waveplate. And the waveplate enacts some unitary transformation on the polarization because the waveplate light moves faster through it if it oscillates along this 45-degree line, and it oscillates slower if it oscillates orthogonally to that. And so in this notation, if we keep 0 as horizontal, 1 as vertical, the generator A would be something like sigma x. And this is roughly a half waveplate, so there's a pi there. And the parameter that we want to estimate is the deviations from pi of this half waveplate. And we can tilt the half waveplate to sort of effectively change its birefringence. And we can make a calibration curve to sort of understand, for a given tilt, what theta do we expect? And using that as sort of some prior knowledge can actually help us get better estimates. But diagrammatically, and in the sort of phase space of this qubit that acts as our probe of this unknown parameter theta, we start with 1, and then we have some displacement. Remember, there's this extra pi here. So for whatever value of theta we get this angle shifted away from 0 in this phase space. Okay, let's come back to version 2 of this demo. The rules of the game are the same. your job is to guess which of these two things is darker. And okay, I'll give you 10 seconds to think about it. This one's still pretty easy. Next time we get to it, it'll be hard. And if I were in person, I would offer to buy lunch to the first person to actually get it right. But I can't do that, unfortunately. All right, so now we're on the hard one. So take 10 seconds. After 10 seconds have passed, feel free to type in the chat which one you think is darker, and I will virtually in spirit pay for your lunch, even though I can't in practice. All right, I have one guess. We have a guess for same. We've got a left guess. Yeah, it's very hard to tell. So is this an impossible task? Am I just being cruel to you to offer lunch for solving this problem? Maybe it's just too much noise in these images to even have a hope of telling them apart reliably. So how can we actually quantify how well we could possibly hope to do in a situation like this? So first, we should say what we mean by how good we can hope to do. So first, we should describe what counts as a good estimator. So our estimator, it should be unbiased. So what I mean is that if we get to do this game many, many times, in the limit of doing it a lot of times, the average estimate should converge to the true value. So we want eventually to be guessing the right value. And given that we have an unbiased estimator, we want the variance of that estimator to be as small as possible. So if our average is correct, and we also make our variations about that average small, we have a good estimator. And finally, we can actually put a bound on how good that variance can be through something called the Cramer-Rao bound and this quantity called the Fisher information. So what this quantity is saying is that theta E is some estimator that I have of theta based on the random data that I get. And the Fisher information is some quantity that quantifies the sort of best case performance I can hope to achieve. And notably, it is not dependent on the estimator that I choose. So just some properties of this Fisher information quantity. It's dimensionful, so it's not like other types of information that you might have seen before that are sort of entropic based, that have units of bits. This has the same, this is inverse squared units of the parameter that you're trying to estimate. And as I mentioned, it doesn't depend on the estimator, it depends just on the distribution itself that encodes this parameter you're trying to estimate. And importantly, if we have n independent identical copies of that distribution, the Fisher information gets just multiplied by n. So in that sense, the Fisher information can be thought of as sort of like an information rate. As I have many, many copies of this and then divide by the number of copies that I get, the amount of information I get per copy, the information rate, is the Fisher information. Okay, and the other important thing about this Cramer-Rao bound is that you can always saturate it, at least asymptotically in the limit of having many copies, using something called the maximum likelihood estimator, which is sort of a popular estimator that experimentalists use all the time. So let's give a concrete example. I suppose I have n copies of a normal distribution. Let's say that I know its variance is sigma squared. Let's say I don't know its mean, and the mean mu is the parameter that I'm trying to estimate. The Fisher information for this distribution is n over sigma squared, and the maximum likelihood estimator I use to saturate this Cramer-Rao bound to eventually get this Fisher information is just the sample mean of that distribution. So pretty intuitive, simple stuff for a normal distribution. And by the way, this is sort of the rigorous reasoning by why we think of statistical uncertainties as going like 1 over root n, because if I take this fish information quantity, 1 over it, and then square root, I get exactly sigma over root n. All right. So knowing now what the best case performance we can ever hope to achieve is, let's come back to this little demo and see whether we had a hope to begin with. So I can tell you some more numbers about it now. Each of these pictures consists of 32 by 32 pixels. There's 100 frames in this little GIF. The intensity distribution is normal, it has a variance of 1 over 400. The scale here is between 0 and 1 for the intensity. The means of one of these pictures is 0.49. The mean for the other one is 0.51. I haven't told you yet which one is the left and which one is the right. But just based on this analysis of the Fisher information, the best uncertainty on the mean we should have is something like 10 to the minus 4. The separation, the contrast between these two intensities is 10 to the minus 2 though. So in this picture, you technically have about 100 times more Fisher information than you would need to tell which one is darker. So why does it not seem that way? Why does it seem very hard to distinguish these two things? Even though the analysis tells us we have 100 times more information than we need. So I won't ask for direct feedback, but take a moment to think about it for yourself. See if you can come up with a reason for why this analysis seems to have failed. And then I'll give my reasoning. So the analysis that we did assumed that you could actually take the sample mean of all of this data. But our brains are not very good at remembering all 100 frames of this image, taking a numerically correct sample mean, and then looking at that number and then comparing the two. Our brains are remarkable at image processing in many ways, but for this particular type of thing, it's not really good at just averaging over those 100 frames that I showed you. So there's a sort of saturation effect going on here, where you can only remember so much, and all of the other frames in this image are kind of redundant information. Well, they're not redundant, they're useful, but your brain isn't really well equipped to handle those. So that brings me to a type of metrology that has recently become popular to think about, which sort of recognizes the fact that in practice, you can't actually use all the information you're given many of the time. In practice, you have to deal with technical noise that might look something like saturation of a photon counter. It might look like limited memory on your computer. It might look like slow noise, correlated noise. It might look like your computer has a slow processing time and you just can't analyze all the data that you have. But in any case, there's become a motivation for looking at data, not in terms of how much information is total, how much could you optimally do, but how much can you actually do based on the trials that you analyzed, that you have the capabilities to actually fruitfully process. So the recipe for post-selected metrology is to first apply some kind of filter, then post-select on trials that survive the filter. And by post-select, I just mean when you apply a filter, there's going to be some trials that survive it, some trials that don't survive it, and we're only going to look at the trials that survive the filter. That's what I mean by post-select. And then finally, we're going to analyze just those post-selected trials. So in essence, what we're doing is throwing away some trials. And so throwing away data never helps you in the optimal case, but we're not really thinking about the optimal case now. We're thinking more practically. And interestingly, throwing away data can increase your information per analyzed trial, even though it can't increase your information per input trial. So this becomes a really valuable tool when you're faced with a difficulty like saturation. All right, so now I'm going to show you the fourth and final iteration of this demo. So imagine that I have some kind of magic filter, which leans into this idea of post-selected metrology. So in the top, I have the same 100 frames that I was showing you before, but imagine I have some magic filter, which only 1 out of 100 of these images is allowed to pass through. But when it does pass through, the contrast gets amplified by a factor of 8. So now we would go from this very hard to distinguish pair of squares to a much more readily distinguished pair of squares. And now you can finally see that the right one is indeed darker. But there's something kind of cute here, which is that the information per input pixel has actually decreased by a factor of 8 squared over 100, so almost half. But the information per pixel that you actually can analyze, I'm assuming that you can really only effectively analyze one frame of these images, has increased by a factor of 8 squared. So again, this has really important practical implications for all kinds of measurements faced with things like saturation noise. But this magic filter looks to be sort of something that I just drew out of my imagination. Is there any way that we can develop this in practice? What kind of tools do we need to make this happen? So here comes the technique that we've introduced in this paper, which is called partially post-selected amplification. I'm going to go back away from this noisy image analogy and dive back into something more closely related to our actual experiment. So we had this polarization. 0 was referring to horizontal polarization. 1 was referring to vertical polarization. It was going through this crystal, acquiring a phase, evolving that polarization vector around. And in this sort of Hilbert space diagram, it's actually theta over 2. But what we're going to do to come up with this sort of magic filter is something quite simple when you get down to it. It's that we're going to filter away some of this horizontally polarized state, but keep all of the vertically polarized state that we can. So we're not just indiscriminately filtering away our photons, we're being very careful about how we do the filter. We want to only filter the horizontally polarized photons and leave the vertically polarized photons untouched. And diagrammatically, you can think of it as squishing Hilbert space along this horizontal dimension and leaving the vertical dimension untouched. When you do that, you actually amplify this angle going from this small theta over 2 to now this big theta over 2. And as a consequence of sort of shrinking your Hilbert space, you also have to throw away some copies of your state. This whole process only succeeds some fraction of the time because this mapping, horizontal going to t times 0 times horizontal, does not conserve probability. So t is going to be just some complex number between this magnitude between 0 and 1. And that's going to be our little knob that we can use to control the amount of post-selection that we're doing, the amount of filtering that we're doing. So to connect that back up to our experiment, we implemented a device that could do this on polarization degree of freedom. And the device is called a partially polarizing beam splitter. You can kind of just buy this off the shelf, but usually you can't make this complex transmission amplitude tunable. So we had to make a little bit of a more complicated device to be able to control this. But in what follows, T is going to be our post-selection parameter, and it's the transmission amplitude for horizontal polarization. And we're going to have to remember the fact that if T is 1, we're not going to do any post-selection. So everything just transmits through this filter. And if T is 0, we've essentially done a full post-selection. So we've just gotten rid of all of the horizontal polarization, and we only have vertically polarized light coming through. And so the way that we can see this is actually a post-selection or a filter by looking at this diagram is that we have a bright source of single photons coming in. It goes into this interferometer, and most of the light will actually be blocked by this beam block here, and only a small fraction of the light will go on to the rest of the experiment to be analyzed. Okay, so now we can look at the full experiment all put together. So we have the preparation that I showed you before. then we have our transformation, which rotates the polarization of our beam. Then we go into this post-selection interferometer. And finally, we actually measure the polarization at a measurement stage. And the one thing I'll remark on is that we can model our post-selection with this operator K. And this is like a Krauss operator, if you're familiar with those. But the useful thing here is that all of this math just takes place in as a single qubit. You don't need to do anything more complicated than just working with the 2 degrees of freedom that I've been talking about, horizontal and vertical polarization. You can capture all the physics that's interesting here with just that. Okay, so let's look at some of our results. So when we actually do this amplification procedure, we get our angles amplified as expected. So in this plot over on the right, we have the true angle that we actually set our birefringence to. And then we have our amplified angle, big theta, that we read out. And so each of these colors will correspond to a different value of t, a different amount of post-selection. The black curve, the black line, is for t equals 1, which is essentially no post-selection. And we just have a straight line that relates true angle with our amplified angle. Okay, recording is in progress, so I'll keep going. So when t equals 1, there's essentially no post-selection, we get a straight line. But as this color gets brighter and brighter, as we decrease t and filter more aggressively, post-select away more of our photons, this curve starts bending up more and more and more. And if you look close to where theta equals 0, we get much, much sharper slopes. And having sharper slopes makes you more sensitive to small changes in this parameter. And that makes it easier to estimate it. On a per detected photon basis, this again comes at the cost of losing many of our photons, but that's okay because, as we saw in the demo, sometimes what you care about is the information per detected photon, not the information per input photon. So again, just more post-selection means more amplification. And another interesting thing about the theory here is that it's technically possible that if your angle was small enough, you could post-select more and more and more. And if you set things up in the right way, you can technically get infinite advantage in your information per detected photon. Here I'm showing you the data that we actually got. Obviously, we don't have any infinite slopes here. You can maybe imagine that if we kept this trend going, we would have an infinitely sharp slope over at theta equals 0. But that's what the theory tells us. The experiment is going to tell us something different. There's obviously going to be something that limits us from getting to infinite information per detected photon. And that's one of the goals we're trying to figure out, is what will actually stop us from getting unlimited information per detected photon. So one of those things is this bias that I mentioned earlier, and systematic errors. So before showing you the next slide, I just want to briefly check up on how bad this bias or systematic errors are going to be. So I'm going to compare the true angle on the x-axis with the estimated angle on the y-axis. And I have a dashed line here to indicate y equals x. So this would be a perfect unbiased estimator. And the colors are the same as before. So black is no post-selection. Lighter colors are more post-selection. You see for the black colors, I'm pretty much on the mark. And for some of the lighter colors, there is a little bit more deviation from this true y equals x line. But for the most part, there's not too much bias here, and we're pretty much on the mark. Especially closer to the smaller angles, you can't even see the deviations here on the plot. And again, I mentioned that this post-selection comes at the cost of some of our photon number. So when we don't post-select, we have about 15,000 photons that we analyze for the experiment. This actually gets done 32 separate times for statistics. So there's technically 32 times that in total. But as we post-select more, the amount of total photons that we have to analyze decreases, but it gets compensated by the amplification increasing the information. So now we can actually look at, now that we've confirmed that our estimator is mostly unbiased, we can now look at the information per detected photon. So in this plot over on the right, again, the x-axis is true angle, now on a log scale. The y-axis is information in units of inverse radian squared. And there's a couple of different quantities being plotted here. First of all, these solid lines are theory calculation for the quantum Fisher information. Quantum Fisher information is sort of an optimization of the Fisher information. The circles are precision, and by precision, I just mean 1 over the variance of our estimates of theta. And accuracy is 1 over the mean squared error of our estimates. And we can see that if we take the solid lines, which again represent no post-selection, we just have sort of this uniform shot noise limited 1 information per detected photon, 1 inverse radian squared information per detected photon. And there's nothing too interesting going on with that line. But as we post-select more, as these lines get brighter and brighter, you can see a trend start to develop. So we start to, information starts to depend on the actual value of theta. And this information starts to climb up quite high. So in the best case, for the most post-selection that we did, we have a precision that's something like 500 times better than what we started with. Again, precision per detected photon. But that does come at the cost in this experiment of some systematic error. So you'll notice that the green square associated with this 500 times enhancement precision is not nearly as good. And that's kind of because this was the limit of our apparatus. We started to run into some systematic errors that stopped us from being able to have our accuracy match our precision. But in other less extreme examples of filtering, of post-selection, we get a pretty good, still quite a good enhancement in our accuracy, about 100 times better. So one of the takeaways here is that, yes, this actually works in practice. You can build this magic filter in the lab, and it will actually help you in terms of information per detected photon. And you also can't get unlimited enhancement in practice because of systematic errors. And interestingly, the same mechanism that amplifies this parameter that we're interested in, that makes this good for detection in the first place, also amplifies the systematic errors. So there's a trade-off between how much you filter, how much you amplify, and the amount of systematic errors you have in your experiment. Okay, so at the beginning of the talk, I was talking about intrinsic uncertainty, which I haven't yet touched on now, but we can get back to that by noticing a key thing about the experiment, which is that the transformation, this half wave plate that generates my polarization change, doesn't commute with this filter, this post-selection that I'm doing. So the way you can see that is I started with a horizontally polarized photon. If I switched the order of these two, if I post-selected first, post-selection would be, my initial state would be an eigenstate of this post-selection operator. I would reduce the number of photons that I had, but it wouldn't really amplify the state. Then I would transform it, and I wouldn't really gain any benefit from this filter. So the ordering here matters. And we know that in quantum mechanics, there's an intimate connection between uncertainty relations and commutators. And so the fact that these things don't commute points to the fact that there's something inherently uncertain here. And that quantity that's uncertain is the rotated state's survival probability of getting through this filter. So the two things that there's sort of an uncertainty relation on are the polarization, whether that polarization is diagonal or anti-diagonal, whether it's oscillating along the fast axis of this waveplate or against it, and whether that photon can actually make it through my polarization filter. So we've gone to sort of a stopping point. We can appreciate what we've covered so far, which is first we had the question of, can we do this experimentally? All right, we can do that. How much can we actually improve in practice? We've answered that. And now we can get to this question of intrinsic uncertainty and how to quantify it. So let's take our favorite two incompatible observables as a way of example, x and k. K is just related to p by a factor of h bar. Let's say we have some state psi. Then psi encodes some marginal distribution for x and k, which you can get by taking some inner products. And it's valid to ask whether these two marginal distributions can be connected together through some joint probability distribution. And you can even ask a harder question, which is, can any combination of x and k be represented by a joint probability distribution? In other words, can some joint distribution represent everything that is represented by psi for these two variables x and k? And famously, the answer is no. And so we have to turn to these things called quasi-probability distributions if we want a sort of phase-space representation. So here I'm going to show you two examples of quasi-probability representations. So in this first column, I have something that is a little bit more familiar to the quantum optics community, which is called the Wigner distribution. And then on the right, we have an object that was the primary interest of this particular paper, which is called the Kirkwood-Dirac distribution. So let's just take a moment to appreciate some of the differences and similarities in the description of a few different states. So the state that I'm going to look at in this first row is the harmonic oscillator ground state. The Wigner distribution describes this as a Gaussian peaked at 0 in phase space, peaked at the origin. And it happens that this state is completely positive. But if I look at the Wigner representation of the first excited state of a harmonic oscillator, we see that that actually goes negative. So the price that I pay for representing these two incompatible observables in phase space is that my distribution has to go negative. Similarly, I have the Kirkwood-Dirac distribution over here on the right. The Kirkwood-Dirac distribution is a little bit of a different approach, but it still encodes all the information that psi does. So for the first harmonic oscillator ground state, I have something that looks like a Gaussian in terms of its absolute value, but the Kirkwood-Dirac distribution is complex valued. And so the color in this plot represents the phase of this quantity. And so I have blue representing negative and red representing positive. And you can see that even for a Gaussian distribution, we have some negative quantities here. So negative quantities in this Kirkwood-Dirac distribution speak to something like coherence, whereas the negative values in this Wigner distribution correspond to something like quantization. Another thing that you'll notice is that whereas the Wigner distribution is sort of azimuthally symmetric, there's no preference for x or p, x or k. The Kirkwood-Dirac distribution does seem to have some preferred directions. So nothing inherently wrong with that, but just keep it in mind as sort of a difference here. And then finally, for the first excited state, we have these 4 peaks. And again, there's some negative values, there's some complex values in there. So it's just to give you a sense of what this quasi-probability distributions are saying. Now we can get a bit more into the meat of this Kirkwood-Dirac distribution. So the original flavor, the one that Dirac initially came up with, was to describe x and k, and you can view that as this sort of trace construction of rho being some density matrix over on the right, an x projector multiplied by a k projector. So it's a very simple formula, kind of in contrast to the Wigner formula, which is quite complicated, involves lots of integrals. And as a consequence of this sort of simple construction, it's very easy to extend this distribution and make multiple different generalizations of it. So you can readily go from, instead of just x and k as your observables, to any two operators a and b. You can just insert b in the trace and a in the trace. From there, you can generalize. You don't even have to talk about two observables. You can talk about any number of observables. I just put more operators in this trace construction. From there, these operators don't even have to be sort of rank 1. They don't have to project onto a single state. They could even project onto a subspace. So it could have a projector onto some eigenvalue A subspace, B eigenvalue subspace. And finally, the sort of next level of generalization that we made in this paper was to go from projectors to POVMs, so positive operator value measures. So now this MA is still a positive operator, but it doesn't have to be a projector. It doesn't have to be degenerate with only eigenvalues 1 and 0. And so by the time we've gone from this top line, the original flavor, all the way down here, we have sort of stopped having a complete description of rho. Depending on the choice of POVMs that you use to represent this Kirkwood-Dirac distribution, you may not actually fully get everything that is encoded in your state, but what you will get is a complete description of any measurement of these different POVMs that you're doing. So anything that could be predicted by the outcomes of these different measurements is jointly described by this Kirkwood-Dirac distribution over all these different POVMs together. So just to go over that a little bit more in detail, again, for this new sort of Kirkwood-Dirac distribution that we introduced in terms of POVMs, POVMs are positive operator value measures. So each of these MIs is greater than or equal to 0, and they sum up to 1. As a consequence of this property, marginalizing over any of these arguments yields the correct marginals because of this fact that each of them resolves unity. There's a nice little trick that you can do to define a conditional distribution from these things that obey Bayes' rules exactly as you would expect. And the final thing is that if all of these POVMs commute with each other on the support of rho, then the distribution is always going to be positive. So as I mentioned before, negative values or complex values in this Kirkwood-Dirac distribution point to sort of coherence between different states, different things that your different measurements would be looking at. So for the Gaussian, we had coherence between X and K. More generally, you could have coherence between different observable states that you'd be looking at. Okay, so that was a very general description of Kirkwood-Dirac distribution. For our particular experiment, we honed in on one particular type of Kirkwood-Dirac distribution. So we're looking at 3 different measurements, 3 different observables or POVMs. One was a measurement of sort of what direction was my polarization going. So that's indicated by this pi a. So this will either project onto my state going parallel to the fast axis of my waveplate or perpendicular to the fast axis of my waveplate. Then in the middle here, I have an operator that indicates the probability of post-selection. So this here is not a projector. It's just a positive operator. Excuse me. And if I just take the trace of this MF with rho, it's the probability that rho survives the post-selection. So you can view this Kirkwood-Dirac distribution as sort of jointly describing what is the direction of polarization for my state before the filter, what's the chance that it survives the filter, and then what's the chance that it is pointing in some direction after that filter. So these different observables are not compatible with each other. Even though this first pi a is compatible with the pi a prime, the post-selection is not compatible with either. And so this distribution can be complex. And we then went ahead and measured this distribution in our experiment. So what I'm showing here, the x-axis is the amplification factor. So this is actually a series of distributions, each at a different level of amplification. And the different colors correspond to different thetas. The y-axis is the quasiprobability. Here I'm just showing the real parts. On the next slide, I'll show you the imaginary parts. And these are laid out in a grid. So kind of like a probability table. This top left here corresponds to the photon being aligned with the fast axis, then being successfully post-selected, then being aligned with the fast axis again. This going one step to the right is aligned with the fast axis, then post-selected. then now aligned with the slow axis. So you can see that these quasi-probabilities, the real parts, are not limited to 0 and 1. We get things that go up to above 70. And it's natural to wonder whether this is actually telling us anything useful. Is there anything that we gain from knowing that our quasi-probabilities aren't between 0 and 1, that they're going up to these huge numbers? And surprisingly, yes. So we can come up with a sort of intuitive quantity that measures how different, how not bounded by 1 and 0 we are, which is I look at the maximum absolute value squared of my distribution and subtract off the minimum absolute value squared. So this quantity would only be at most 1 for distribution between 1 and 0, but because I can have things going up to 80 and down to minus 80, this thing can get arbitrarily large. So the piece de resistance of this work is now plotting this non-causality gap together with the deficient information that we measured. So this plot has that data in it. On the x-axis, I have my post-selection parameter. Over to the right is no post-selection. Over to the left is a lot of post-selection. On the y-axis, I have my information that I get. The crosses denote the quantum efficient information that we got in our experiments. The solid lines are the theory, and the stars are the non-causality gap that we measured. And so you can see there's this beautiful agreement between the quantum efficient information, which is this very sort of experimentally minded quantity. It's something that's related to this parameter estimation task. And then we have this non-causality gap, which is something that comes from a object in quantum foundations. So these two things really have no business matching up with each other. One is about how well can you estimate a parameter, and the other speaks to this inherent uncertainty in quantum mechanics that you can have between two observables. And yet there's this beautiful agreement between them. So I'm getting towards the end here, but the one thing that I'll mention is that getting this huge boost in information per detected photon doesn't actually come at a huge cost to the information per input photon. So you can see that even when we post-select quite a bit, we still have information per input photon still hovering around the 1 mark. It doesn't come at too much of a cost in terms of per input photon. Okay, so we've now gone through everything that I had promised. We now understand how the improvement depends on the intrinsic uncertainty. And we now understand how we can quantify that intrinsic uncertainty through this non-causality gap of the Kirkwood-Dirac distribution. All right, so with that, I'll go ahead and end and just thank you guys for listening. And again, thank my collaborators on this. And yeah, I'm happy to take questions.
Thank you very much, Noah. This was a really great talk. I especially liked your very kind of new and unorthodox ways of explaining the filtering technique and the kind of Fisher information and stuff like that. So that was great. If anyone has any questions, please put them in the chat or under the Q&A button, and then Noah will be able to answer them there. I see Hugo already probably has a question.
Hi, yes, I do. This was a really nice talk, by the way, and I like the way of presenting the slides. So my question is a bit, I guess, when you talk about enhancing the differences or using uncertainty to enhance the differences and extract more information, how can you make sure that the information you're extracting is correct? And so if I use your example of like highlighting the contrast between those two images, how do you know you've picked the right contrast to amplify and that you're not going down the wrong way?
Okay, so yeah, there's a lot of parts and subtleties to that question. So the first thing is that we kind of on the outset, I'll say the theory that we originally did was just about sort of precision and variance, and it wasn't saying too much about whether our estimator would still be unbiased or not. It kind of took doing the experiment to see whether this amplification would actually hurt the bias or not. And so that's why a few slides back, I showed you just a sort of quick sanity check to seeing whether doing this implication hurt our bias or not, whether it increased our systematic errors. And it does to some extent. But there's a trade-off that you can balance off. So if you have a good idea as to the level of your systematic errors, you can get a sense of how much it's safe to post-select by, still get the enhancement in precision without introducing too much additional systematic error. So the quick answer to that is we didn't until we did the experiment. And now having done the experiment, we know that there's sort of a sweet spot where you can get a good enhancement in precision without sacrificing too much in missing the mark too much.
Okay, and can you comment a little bit on like physically what does this sweet spot mean, or
Sure.
what? Yeah.
So physically, what it means is, let's see if I can go back to my picture. Yeah. So the mechanism here again is pretty simple. We're just kind of squishing Hilbert space, and that's amplifying the angle. But imagine that instead of this being my true theta over 2, that my angle, that my vector is rotated from 0, there's just a systematic offset in where that was placed. Now that gets amplified by this, and that systematic error gets amplified, and I have to be concerned about that when I am looking at my statistics. So the intuitive explanation for where the sweet spot is you want your amplified systematic error to still be smaller than your statistical variance. And so just having a good sense of what your systematic errors are before having done the post-selection gives you a sense of how much post-selection is safe to do. And something that's interesting there is that this amplification of systematic errors is not actually all that bad. It's not all strictly bad, because it can actually help you find the systematic errors in the first place. If they're so small that you wouldn't have noticed them without the amplification, this actually will bring them out for you. And when we were setting up our experiment, we actually found this helpful. So as we sort of were aligning that waveplate that generates my phase rotation, after doing the amplification, we realized, oh, we actually set that up a little bit wrong, and we tilted it a little bit in conjunction with some measurements, and we got actually to reduce those systematic errors. But the short answer is the sweet spot is that you want your amplified systematic errors less than your statistical uncertainty.
All right, thank you.
See that Professor Barnes has a question as well.
So there's a telephone going off in the background, but I'll just ask my question and ignore the telephone. So each photon that comes through the system, it needs to be heralded in order for you to post-select. Is that correct? So you couldn't use this for sort of night vision or something like that?
Oh, no. So the great thing, let's go back to the setup. So I have a heralded single photon source, but that's really just to make sure I can do photon counting, and that helps with the statistics. But the filter itself has a beam block on one of the ports. So I don't actually need to, the only sort of heralding that I need to do is to see that I got a photon at my measurement stage. But I don't need an extra step to see whether my photon survived the filter or didn't, because my beam block just blocks all the photons that didn't survive the filter.
Right. So you could then use this in sort of, you don't need a single photon source. You can do a reflectivity measurement for like a Kerr effect measurement with something like this.
Yes, but the thing that you have to be careful with, and the important thing is that you can't just use any old filter. the power of this technique really comes from sort of intrinsic uncertainty that you're exploiting. So your filter that you use has to not commute, has to be incompatible with the generator of your parameter of interest. So if you have some sort of night vision goggles and you somehow exploit the wave properties of light and come up, exploit the incompatibility of some properties of that light, yeah, you maybe could devise some kind of cool night vision goggles that use this effect. I don't know what the details of that would be, but certainly there's applications for this in all sorts of different parameter estimation schemes. And David actually has a paper that he's been working on that generalizes this to not just one parameter of interest, but multiple parameters of interest. So there's ways that you can sort of take this and fly with it. And then the one other thing I'll say is that this idea of concentrating information from many input photons onto a few that you retain at the end of the post-selection is not fully new to this work. There's a related technique called weak value amplification that this technique is kind of a cousin of. And there's some similarities and differences between them, but I'll just have that disclaimer that we're not the first ones to come up with this kind of a process, this kind of filter.
Right. Okay. Anyway, very, very interesting talk. Thanks very much.
Thank you.
Do we have a question from Chris? Is that the case?
Yeah.
Yes. Hi, thank you for the talk. So I was wondering, so the idea is that you're condensing the information into less photons, I guess. And so does that, is the reason you can't just continually get more and more gain because if you wanted, say, like some ridiculously high gain, then you would have to throw away effectively all of your photons, and so you haven't got anything to measure. Is that the kind
That's right,
the way
that's
it's working? Okay, that was my question. I just wanted to make sure I understood that.
Yep.
Thank you.
Yeah, so there's sort of a data processing inequality, which is that there's nothing that you can do once you have your parameter encoded on a state, there's nothing you can do to that state to actually increase the overall information in principle that you can achieve from it. But you can do things that will make it easier to extract that information in practice. And so that's what we're doing here.
I think that the data inequality is called the no free lunch theorem.
Yes,
right?
also that one.
Yeah. I think Stefan de Bievre has a question. Is that right, Stefan?
Yeah, I do. You hear me?
Mm-hmm.
Yes, okay. So, well, thanks for a very nice talk. I really enjoyed this very much. I have a probably naive question. You mentioned that the KT you introduced is like a Krauss operator. So I was wondering, if you just look at the mathematical model, what do you have in mind? How does this post-selection act on an arbitrary density matrix? So I'm used to Lindblad generators and things like that, and quantum master equations, but they always preserve a probability. And so here you just say, well, okay, this thing doesn't preserve probability. What is sort of the framework? What is the mathematical model you're using?
Yeah. So mathematically, if I want to model this operation, I would have, if I have a pure state, I would just do matrix multiplication of this k of t on my psi. If I have a density matrix, I would do the left multiply by k of t, right multiply by k of t dagger. And that doesn't conserve probability. So to conserve probability, what I do is I just sort of renormalize the state. I divide by the trace of the state after having applied this operator. And essentially, in practice, what that really means is that when I do my photon counting over at this measurement stage, I'm sort of looking at the amount of photons that hit this detector divided by the sum of the photons that hit these two detectors. So in that sense, I'm sort of renormalizing by the probability of getting a detected photon rather than the number of photons that I had coming in from my input source. Does that answer your question? Maybe you're answering a more in-depth question than I answered.
No, probably not. But the way you seem to explain it, it mixes the post-selection and the measurement. I thought you had the the postulate, I thought, but I mean, I'm just trying to speculate here. The transformation part, of course, I understand that's the usual unitary thing. And
Yeah.
then you have a post-selection, and then you do the measurement. But now you explain, you seem to, you normalize after measurement. We always need to normalize, but now you seem to sort of do the post-selection and the measurement at the same time and normalize at the end or something. I'm not sure I understand.
No, so maybe I led you astray, but the post-selection really is just this beam block. So it's the fact that we don't measure this other beam of photons that comes out from this constructing this filter. And the renormalization happens at the measurement stage, where I just divide by the number of photons that I actually detect. But so I could model this as a sort of probability conserving thing if I looked at all the photons and included the photons that hit this beam block. So I can model this whole thing in sort of the church of the larger Hilbert space. I could describe this cross operator as a unitary interacting with some sort of bath state, which would be this extra path here. And that would all be fine and dandy. But doing that extra, expanding my Hilbert space and viewing it as a probability conserving thing doesn't really change any of the physics. It just adds some extra dimensions of to the Hilbert space. So we chose to do it in the sort of simpler, more not pragmatic, but more concise, I guess, model. Fewer dimensions is better.
Okay, well, thank you. Is this described in detail in the paper?
Yeah, yeah.
Okay. Thanks.
Okay.
Okay, I think I don't see any more questions. So I think it's time to properly and really thoroughly thank you, Noah, for waking up at this early hour and giving such a great talk and answering to all our questions.